So hello everyone, welcome to another particular series of our organic chemistry course. So today we are going to start about organic spectroscopy, and in this particular series we are actually focusing on IR and NMR spectroscopy for the organic spectroscopy perspective. Okay. So first let us talking about the context. So where we will discuss in this particular long enough series. So here in this particular lecture series, we are initially with the general introduction, where actually I will show about some kind of spectroscopy and as well as the electromagnetic radiation in brief, and give us a small quantum mechanical analysis that actually that much actually required for the organic spectroscopy point of view, not the physical spectroscopy point of view, but organic spectroscopy point of view to generate the importance and generate the understanding of the particular subject. So then we'll move on to the IR spectroscopy. We are actually covered the IR spectroscopy in detail, where basically we begin with our IR spectroscopy course with the physical interpretation of vibrational spectroscopy. That is nothing but a IR spectroscopy. Then we are talking about the infrared spectroscopy and mode of vibration, important IR peaks and factor affecting IR peaks, and then some question answers. Similarly, we move on the NMR spectroscopy. First, we are discuss about the theory. Then we are talking about the 1H spectroscopy as well as 13C spectroscopy. And organic spectroscopy chapter is a very important chapter for your exam purpose. The most weightage come from organic chemistry is from spectroscopy. So you have to learn the spectroscopy subject very minutely, and you have to practice this particular question from NMR spectroscopy as well as IR spectroscopy very cautiously, because this chapter actually gives a chunk of numbers in the examination. So let us begin with our first lecture, that is the general introduction on electromagnetic radiation. Okay, so first we began with our discussion with spectroscopy. First, by definition, spectroscopy is a study that how matters interact with light, and the light is nothing but electromagnetic radiation. And by studying the empirical study, by conducting the empirical study that how light matter interacts with the light, we used to determine the structure, composition, and properties of substance. Okay, so this is the broad or simplest definition of spectroscopy. Now, many people has been confused about what is spectroscopy and spectrometry. Some of the students are actually think about that the both term, the spectroscopy and spectrometry, both are in the same term, but actually they are not. Like spectroscopy and spectrometry have their own different meaning, and I want that from the first slide itself you have to know that what is spectrometry and what is spectroscopy actually. So in a very basic manner, if we are to explain you in a very basic or very brief way, then I can say that spectroscopy is a study or science of study how light and matter interact. Like this is not a concrete study, it is an empirical study. Like we actually through a third person observer that okay, so light is uh, put on this particular matter and how the matter interact, we are actually learn that particular thing. Whereas the spectrometry is a tool or method or instrumentation by which we actually or the people or the scientists actually determine the quantitative changes in the particular matter. So we can say that spectroscopy is an empirical study and the spectrometry is the same thing but applying certain instrument to get the quantitative analysis of the particular light matter interaction. So this is the very much difference about the spectroscopy and spectrometry, and I hope that you will understand that particular thing. For example, IR and NMR, what we are doing here, it is a spectroscopy, but mass is spectrometry. Okay, so you have to understand this particular thing, like mass spectroscopy, it's not a spectroscopy, it is a mass spectrometry. But IR is spectroscopy, NMR is spectroscopy. Okay. So let us move on to the next slide, that is called about electromagnetic radiation. Like electromagnetic radiation, if you want to know that, basically it is an a perpendicular distribution of a electric field and magnetic field. Like you can see here that electromagnetic radiation is energy that travels through space or oscillating electric and magnetic field, and it is moving at the speed of light. It includes a range of wavelength from radio wave to gamma waves depending upon their wavelength and as well as the energy. Okay. So what happened that it is a three-dimensional where the electric field oscillates in, example, it is a oscillate in the z direction, and the magnetic field that is oscillate in the y direction. So both the uh, perpendicular field are actually shows the electromagnetic propagation in the x direction or the perpendicular pathway. So this is the electromagnetic radiation, and if you find here that from here to here is actually become one wavelength. Like here a wave starts changing its phase, it changes phase and then again return to this particular part. So the distance required a wave to get their actual amplitude, or you can say the actual space, is called term as the wavelength. Okay, and depending upon the various wavelength, it has a different energy, and from there actually we got the electromagnetic spectrum from gamma waves to radio waves. Okay, so this is the electromagnetic spectrum. Okay, now here it is written that electromagnetic radiation can be classified based on wavelength into different region of the electromagnetic spectrum. Like here you can see that as we go from left to right, the wavelength is increasing. Okay, and depending upon the wavelength increasing, there is a certain different region is generated in the electromagnetic radiation, such as gamma rays, X-rays, UV, and visible light, infrared, and radio waves contains radar, TV, FM, and AF. So here you can find that as the small wavelength is there, that means the frequency is much higher. Okay, and as the wavelength getting much more longer, then the frequency is getting lesser. So we will discuss in the when we discuss about the Planck equation and all. So just you have to understand that depending upon the various wavelength, okay, the electromagnetic radiation can be classified in different sets, such as radio waves, and the radio waves have highest wavelength. Microwaves is there, infrared is there, visible light is there, ultraviolet is there, X-rays is there, and gamma rays is there, obviously. Okay, so now it is talking about the Planck equation. Planck equation suggests that E equal to h nu, where E contains the energy and nu is the frequency. That means more the frequency, more the energy of the particular electromagnetic radiation, and the h suggests the Planck constant, and we know the Planck constant value 6.626 in 10 minus 34 joule second. Okay, and similarly we know that frequency is nothing but c by lambda, where c is the speed of light and lambda is the wavelength. So here if we check about again the the electromagnetic radiation spectrum here, then we can found that here the X-rays and gamma rays, which have the higher frequency, that means it contains higher energy. From the Planck equation we can discuss that particular thing. And similarly, since it is a higher frequency, and also we know that energy and the wavelength have their anti-proportional relation, that's why that higher energy which suggests the lower wavelength here in this case. And here if we go from this particular side, wavelength is increasing, that means energy is decreasing, and is energy is decreasing, that means frequency is decreasing. So we can say that gamma rays and X-rays having the higher energy, whereas the microwave and radio waves has the lower energy. And depending upon the energy difference, actually this particular rays, or we can say the waves, actually shows different light matter interaction, and depending upon the different light matter interaction, we are actually getting different spectroscopy. Okay, so here you can find that X-rays and gamma rays. So let us show here one bond. Okay, now X-rays and gamma rays have so much energy, then when actually it is irradiate with some kind of organic molecules, this particular bond breaks apart. Like we know that by breaking one particular bond, like if a particular energy is greater than the bond dissociation energy of the particular bond, then the bond getting cleaved. So what happens that X-rays and gamma rays having so much energies that they can easily break this particular bond, and thus these two particular are not shows any kind of spectroscopy, but they are actually shows some kind of spectrometry or some kind of crystal analysis part where actually this thing is important. Now here in case of UV ray have some kind of UV rays, like UV have their own classification like UVA, UVB and UVC. So what happened that UV that contains the 254 to 300 nanometer wavelengths. So what happened that these are not able to break the bond ideally, but they will show the some kind of electronic transition. Now in a molecule there is a three different transition observed. There is a electronic transition, a vibrational transition and rotational transition. Okay, so what happened that they will discuss in the next slide. Okay, like the quantum mechanics of the particular bond. But before that, let us understand that UV are actually not capable to directly cleave the bond. In basically the UVC, okay, the higher wavelength UV, but it will be responsible for electronic transition. Like it has certain energy, then one electron from the E0 state can easily jump to the E1 state and vice versa. Visible region, this our how we can see the world, like how we can see the colors and all, we can show the visible region. And visible region, we can say that some molecule like KMNO4, it is shows the purple in color, like there is a kind of LMCT DD transition is there also, we can learn in this particular thing in the coordination part. So this type of thing actually observe in the visible spectrometry, physical spectroscopy part. Okay, but they are not entirely classified in spectroscopy. Actually, there is a mergified of UV visible spectroscopy. UV visible is the direct a mergified spectroscopy. Like these two regions are actually merged in the UV spectroscopy. Now, infrared spectroscopy have more higher wavelength, and since it is have the more higher wavelength, that means it has lesser energy comparatively UV and visible. That's why it is not able to do the electronic transition, because the energy gap between electronic transition is much higher, but it will show the molecular vibration. And depending upon molecular vibration, we are getting the IR spectroscopy that will be discussed in our next class. Then comes to the microwave. Microwave are basically responsible for the rotational transition. Like in an electronic state, there contains n number of vibrational state, and between two vibrational state, there is an n number of rotational state present. And the microwave is actually responsible for the rotational transformation, and this is important in the physical spectroscopy part, not in the organic spectroscopy as such. And the radio waves is the highest or the longer wavelength, but it has very lesser energy. So they are not able to do the rotational transition, but they can show the spin flipping. And this is actually the interesting point that we will learn in the NMR spectroscopy here. So I hope this particular slide is clear for you. Now let us talk about the quantum mechanics, or understand the quantum mechanics of spectroscopy. As I already discussed, that this is the two electronic energy state. Now between these two electronic energy state, there is a n number of vibrational energy state is there. This is the n number of vibrational energy state is there, and between two vibrational state, there is a n number of rotational energy level there. Now we know that the quantum mechanically a transition can be observed when the EMR or electromagnetic radiation have equal energy gap delta E is equal to h nu. That means the energy of the light or the electromagnetic radiation is equal to the transitional energy. Then the transition has been observed. Now in the case of UV light are actually capable to do this type of energy transition. That's why the one electron actually jumped to from E0 state to E1 state. Now what happened that in the case of IR, okay, in the case of IR are actually capable to do this transition, like one vibrational state to another vibrational state in the same electronic state. And the radio waves or microwaves are actually capable to do this transition state where between a two rotational energy level between certain two vibrational energy state. So here it is written that as per the quantum mechanics, the energy level is not continuous, it is discrete in nature, and due to this discrete, we know that about the Bohr model that the transition has been observed between two energy levels when the photon energy is equal of the transitional energy, okay, or the electromagnetic radiational energy is equal to the transitional energy level. Now, quantum mechanically says that between two energy level, there is a n number of vibrational state is present, and between the two vibrational energy level there is a n number of rotational state present, and depending upon the EMR energy different transition observed which yield different light matter interaction, that is different spectroscopy. Okay, now let us dive down in the much more quantum mechanically part. So harmonic oscillator says that the electronic transitions are not in the straight line pathway. It shows a Morse potential curve. This curve is called the Morse potential, where this is the our E0 state and this is the E1 state, and this is the nothing but a anharmonic oscillation approach. So when you learn about quantum mechanics, there is a concept of SHO, that simple harmonic oscillator. This is the extended version of simple harmonic oscillator where actually this type of things has been introduced. So what happened that between two energy level there is a n number of vibrational energy level is there, and vibrational energy level is basically observed between these two. Like example, it is the diatomic molecule. Now this particular bond actually come straight or goes apart. So due to this actually it is shown a oscillating motion, like it is come here, come back, come here, come back. Okay, and based of this particular thing, based on this type of oscillation, this type of curve has been observed. Now when the oscillation level is much more elongated or the much more energy I get, yeah, this the bond between this oscillation actually cleaves apart, and thus we got this type of Morse potential curve. Like here this particular bonds actually breaks apart, or we can say this is the dissociation energy of a bond. This is a bond dissociation energy. Okay, so what happened that if any kind of electron present here and it will get a UV light of the energy is equal to the this particular transition, then this particular E is getting transition. Now it's not necessarily important that a zero level energy or E0 V0 level of electrons are actually jump to the E1 V0 level of energy state. It can go any kind of vibrational energy level as in presence of the E1 state. Okay, this is the UV case. But in the case of IR, what happened that it will actually vibrate between same electronic energy level but different vibrational level, depend upon the what kind of the energy of the particular IR or particular EMR given to that particular molecule. And the rotational is simply between the two vibrational level, there is a n number of rotational level is there. So the movement of the electron is between these two energy level. I hope it will be understand. If not, then I would suggest that rewind the particular video and if possible slow down. I hope you will understand this particular thing. Okay. So with this, we have to end this particular class. I know this particular class is so much haphazard, and if you are not familiar with the quantum mechanics and the SHO model, it might be confusing and complex for you. But just take a empirical idea of the spectroscopy, like it will not that much important for question solving, but it is important for the understanding part. So thank you for listening.